Hey guys, so we're going to do the notes for chapter 6 section 2, which is over inconsistent and dependent systems. So from 6.1 we learned how to use the Gaussian and the Gauss-Jordan elimination methods in order to solve for our systems of equations. So today we're just going to use the Gaussian method in order to solve these systems and determine if we have inconsistent or dependent systems. So our first example, which we're just working problems, there's not really notes for this one, it's just working them out and seeing what happens with them. So we have x minus y minus 2z equals 2, 2x minus 3y plus 6z equals 5, and then 3x minus 4y plus 4z equals 12. That's going to be the system that we're going to look at first. So remember, step one of using the Gaussian system of elimination is to write an augmented matrix from our system of equations. That's where we write the coefficients of our system using the vertical bar, which makes it an augmented matrix, with the answers or what's on the right-hand side over here on the right-hand side of our bar. So we get 2, negative 3, 6, 5, 3, negative 4, 4, and 12. Now remember, when we're using the Gaussian system of elimination, the whole point is to get to the row echelon form, which is where we have ones down the diagonal, zeros underneath the ones, and then we have numbers and the other spots. So this is our goal. We want this matrix. So here's the nice thing is we already have a 1 in this upper right or upper left-hand corner. So that's good. So the first thing we need to do is think about how do we get a 0 right there. This is where we multiply one of our other rows and then we add to it. So what do I need to add to get it to 0? Well, I need to add negative 2. So is there one of the rows that I can multiply by in order to get a negative 2 when added? And the answer is yes, the top row. So if I do, let me scoot that over so I have room to write. If I do the top row times negative 2, and then I add that to row 2, that's going to give me a 0 here. So my top row stays the same. My bottom row stays the same. It's just my second row that's going to change. Because remember, this part right here, the second one tells you what row you're changing. So I have negative 2 times 1, which is negative 2 plus 2 is 0. Negative 2 times negative 1 is a positive 2. So that's going to be a negative 1. That'll be 4, which gives me 10. Negative 2 times 2, negative 4, which gives me 1. Okay? So I need to get this to 0. Again, you need to think about the same process. What do I add to 3 to get it to 0? Well, you add negative 3. So is there a row that I can multiply by in order to get that to be negative 3? Yes, this top one, because there's a 1 there, you can multiply it by the negative 3 and then add it to row 3. I'm going to slide this down so you can see the next matrices. So if I do negative 3 times the first row and add it to the third row, that'll give me my new third row. So my top row stays the same. My second row stays the same. It's this third row that's going to change. So negative 3 times 1 is negative 3. Add 3, that gives me 0. Negative 3 times negative 1 will give me a positive 3. Add that to a negative 4, it gives me negative 1. Negative 3 times negative 2 gives me a positive 6. Plus 4 will give me 10. Negative 3 times 2 is a negative 6. Plus 12 will give me a positive 6. Okay? So the next thing I need to have this be a 1. So when you're trying to get your diagonal of 1s, you're going to end up multiplying by some sort of a non-zero number to that row. So what do I multiply -1 by to get 1? I multiply it by -1. So I'm going to do negative times everything in row 2 to switch that over. So my top row stays, my bottom row stays, and then everything in my second row gets multiplied by a -1. Okay. Then I need that to go to 0. So what plus -1 gives me 0? Well, it's a +1. So here's the nice thing is that I can just add. I don't even have to multiply because my R2 has a +1 there. So I can do R2 plus R3 to give me my new R3. That's an R. I don't know why I keep wanting to change it to a B. Can you see that? Yes. But I am going to scoot you down a little bit because we're going to be down here. Okay. So my top 2 stay the same. 1, 0, -1, 1, 2, -10, 2, -1. Okay, I'm just adding my R2 and my R3. So that gives me 0, 0, and I have a -10 and a +10. That gives me 0. And then -1 plus 6 will give me 5. Okay, so this is weird. And I drew a face and a big thing in my notes. It looks like that. So it's like, uh-oh, what is going on? What this says is we have 0x plus 0y plus 0z equals 5. So we have 0 equals 5. Is that true? Does 0 equal 5? That's not true. That's false. Because that's false, this is an inconsistent system. It doesn't work. And we kind of knew that actually back over here in this step. If you notice, we had 0, -110, 0, -110. Well, remember, when you're dealing with matrices, you're able to write those as equations. That tells me that I had -y plus 10z equals 1 and -y plus 10z equals 6. Well, since these are the same thing, that's like saying 1 equals 6. But that's not true. And because that's not true, this tells us it's an inconsistent system. So there's no solutions to that system of equations. Remember, chapter 6.2 is all about inconsistent and dependent variables or systems, and this is how you get an inconsistent. On 6.1, all of ours came out to nice solutions, which means they were consistent. This one, we get something that's false, so it's not consistent. Okay? I'm going to leave you down there for a minute while I come and write the new problem over here. And then I'll move you back over here. Move you. I'm starting my new system of equations. As I told you, today is really just about working examples to see the inconsistent and the dependent systems. It also gives you a lot of practice of using Gaussian elimination, which is good. So there's our new system. I'll let you copy that down while I erase the board. Okay, so our new system is right here. Again, we're going to use the Gaussian elimination. We want to get the row echelon form as we continue. So the first step is to simply write the augmented matrix using the coefficients of our equation. Sorry, I had a brain freeze for a minute for some reason. So 3, -4, 4, and 7, 1, -1, -2, and 2, 2, and -3, 6, and 5. So remember, the first thing that we're wanting to do is we want to get a 1 in that upper left-hand corner. The last example we did already had a 1 up there, but this one doesn't. So we want to get a 1 up there. So remember, we have 3 different row operations that we can do. We can multiply and add our rows. We can multiply by a non-zero number in a row, or we can simply just flip-flop our rows. So if we want a 1 up here in this upper left corner, the easiest thing to do is just flip-flop row 1 and row 2. So I'm going to do row 1 is going to go to row 2 and vice versa. So row 3 stays. And then my row 2 is going to move up. 1, -1, -2, 2, and my row 1 comes down. Now I need to think about getting this to a 0. So again, what do I add to 3 to get to 0? Well, I add -3. Sorry, let me scoot you down. Okay, so I add -3. So can I multiply one of my rows by something to get -3? Yeah, the easiest one is to multiply the top. So I have -3 times R1 plus R2. So my top stays 1, -1, -2, 2. My bottom stays 2, -3, 6, and 5. And then my row 2 is what's changing, and I'm taking -3 and I'm adding it to my row 2. So -3 times 1 is -3, plus 3 is 0. -3 becomes a 3, becomes a -1. That becomes a +6, which will give me 10. And that's going to become a -6, which will give me 1. Okay. So next I need to focus on this spot, and I need to get that to be a 0. Same exact principle as the first one. A lot of times I'll actually even do these in the same thing, where over here I just write -2 R1 plus R3, and I'll do them in the same setting. So if you look at my notes online, that's what I do, but I do write out my explanations. So I'm going to do a -2 times the first row, and I'm going to add that to the third row in order to get that to a 0. So my first 2 rows stay the same. So -2 times the first row, and then add this row. So that becomes a -2 plus 2 is 0. +2 plus a -3 becomes a -1. -2 times -2 is a +4, plus that equals 10. -2 times 2 is -4, and that becomes a 1. Okay. So the next step is I need to get this to be a 1. Remember, when I want something to become a 1, I'm going to think about what can I multiply it by to get to a 1. So what do I multiply -1 by in order to get a +1? Well, I multiply it by a -1. That means I'll have a -R2, and my top row stays the same and my bottom row stays the same. So 1, -1, -2, and 2, 0, -1, 10, and 1. Still see that, but I'm going to move you because you're going to need to be moved anyways. Okay, so negative times my middle row, so negative times 0 is still 0. -1 times negative is 1. That'll become a negative 10 and a negative 1. Okay. So now I want this to go to 0. So can I multiply or just add a row to that that's going to make it 0? Yeah. If I add row 2 to row 1 or row 3, that's going to give me 0 there, which is going to be real nice, and it'll go away. So I don't even have to multiply this time by any number. I can just do R2 plus R3. So my first 2 rows stay the same. We're getting really wonky, sorry. So add R2 and R1, so that gives me 0. 1 plus a negative 1 gives me 0. Negative 10 plus 10 gives me 0. Negative 1 plus 1 gives me 0. And again, in my notes, I address this with a big what? What just happened? Well, it says 0x plus 0y plus 0z equals 0. So 0 equals 0. Is that true? Yeah, that's always true. Well, we're not quite done though, because we still have this. So let's look at that. Let's look at that smaller matrix now. Let's just eliminate that third row. We have 1 minus 1 minus 2, 2, 0, 1, negative 10, negative 1. So there's our smaller matrix. We just took out that bottom row, because the bottom row doesn't really give us anything because it says 0, 0, 0, 0, 0. So we did get our, like this is a smaller Gaussian, right? We have the 1s with the 0s underneath. So let's write our new system from this. So this says x minus y minus 2z equals 2. And y minus 10z equals a negative 1. So before, when we've done Gaussian elimination, we get all the way down to where like z equals a number, and then we just back substitute, right? Well, that's not quite what we get here, but it's pretty close, because we have 2 variables now. So we can solve in terms of our y. We can say y equals 10z plus 1. All I did was add my 10z over. Now that I have a value for my y, I can plug that in here and figure out in respects to, like, what my x is in respects to z. Basically, we're solving this. Instead of getting numbers, we're going to get everything with respects to z, so that once we know what z is, then we can figure out everything else. So I have x minus y minus 2z equals 2. That's what this top equation or the top line of my matrix was. So now everywhere that there's a y, I'm going to put in a 10z plus 1. Right? Yes. So I have x minus a 10z plus 1 minus 2z equals 2. X minus 10z minus 1 minus 2z equals 2. X minus 12z, I'm going to add that 1 over, equals 3. Wait a second. Oh, that's a minus 1. Sorry, y equals minus 1, minus 1, so that becomes a plus 1. So I subtract that 1 over, and I get 1. Sorry about that. I lost my negative up there, which happens. So now I have x equals 12z plus 1. You might be like, well, great. I don't know what that tells me. Well, we have y equals 10z minus 1, x equals 12z plus 1. So we don't know what z is because z went away, but we do know everything else in terms of a z. So again, my x was 12z plus 1. My y was 10z minus 1, and then my z is just whatever my z is. We don't know because it's going to depend. This is a dependent system. Your x and your y values are very dependent upon what your z is. If we don't know what z is, then we don't know what x and y are. And we get dependent systems when we have a whole row of our matrix just go away, which is what we had happen. That made everything go away. So let's do another one, okay? I think you'll, I have no idea if you're getting it because you're on the other side of a computer screen, but I can hope. All right, let's come down here and we'll do one more example. And then what I'm gonna do is I actually have two other problems, but nothing changes in them. So I will do another video that has just the extra problems on it that you can view if you want to see them. (3x plus 7y plus 6z equals 26. X plus 2y plus z equals 8. So I'll let you write that down while I erase the board. So you get an inconsistent system when you get something that's not true, like 0 equals 5. You get a dependent system when a whole row of your matrix goes to 0, because that's always true. I mean, 0 equals 0 no matter what. So we're going to do this one now, which starts off with just 2 equations instead of 3, but we still have 3 variables. So the first step in Gaussian elimination is always just to write your augmented matrix. 3, 7, 6, 26, 1, 2, 1, 8. So remember, in Gaussian elimination, we want a 1 in the upper left corner. Right now we have a 3, but if we just flip-flopped our rows, then we would have a 1 in the upper left corner. So I'm going to flip-flop my R1 and my R2. I have 1, 2, 1, 8, 3, 7, 6, 26. So now I have to think about how do I get this to go to 0? 3 plus what gives me 0? -3. So that means I need -3 times R1 plus R2. That means my R1 stays the same. -3 times R1 is -3. That goes to 0. -6 plus 7 is 1. -3, 3, and then -3 or -24 plus 26 will give me 2. So this one worked out really simple in that it started with 2 equations with 3 unknowns, but very quickly we get a 1 and a 1 in our diagonal, even though it's not quite a straight, complete diagonal because we don't have that third row, but that's okay. Because what we know now is that this is going to be a dependent system where we're going to have everything in respects to z again, just like we just did before, because we only had 2 equations to work off of anyways. So from this matrix, since I have my slightly skewed row echelon form, I can write my system again, where I have x plus 2y plus z equals 8. And then I have y plus 3z equals 2. So y then equals a negative 3z plus 2 if I move that over. And then I can substitute that. I can back substitute that up here, where I have x plus 2 times my y, which I just said was negative 3z plus 2, plus z equals 8. Distribute that 2 in. Combine my like terms and move my constant over. So I have x minus 5z equals 4, x equals 5z plus 4. So that means that my solution for this, since it is a dependent system, well, my x is 5z plus 4, my y was negative 3z plus 2, and then my z is whatever my z is. But my x and my y values are dependent upon whatever my z value is in this case. So that is dependent and inconsistent systems. Again, I'm going to do another video with, I think, two extra problems. So one more example each of an inconsistent and a dependent system. So if you want to watch that next video, it'll be up shortly.